let's apply our curve fitting technology to the results of another experiment. What we're going to do is to fire an arrow at a target. So as we notch the arrow on the bowstring and we pull the arrow back, getting ready to release it, the arms of the bow are bending, and this is sort of another example of a very powerful spring at work. And when we release the arrow, it will fly to the target. And what we've done is we've taken a bunch of measurements. So as the arrow flies up and then falls back down and hits the target, we're going to be measuring the height of the arrow at various times during its flight to the target, and working to fit a curve to that, so you can come up with a mathematical equation that describes the flight of the arrow. We'll also be looking into ways of measuring how well our curve is actually fitting the data. Up to now, we've been sort of eyeballing it, which was a good start, but we can actually develop some sensible mathematical measures that will tell us about the goodness of the fit.
Here's some Python code that lets us experiment with the data we got from firing the arrow with the bow. As before, we have a procedure that helps us get the data out of the data file and put it into a bunch of lists. In this case, what we have is a bunch of distances at which we made the different measurements, and then for each distance we have the heights at that distance from 4 separate experiments. To actually do the curve fitting, here we have tri-fits, which is very much like the routines we've written before. We're converting the distances which were in yards into feet, and then we're going to process the 4 measurements from each of the experiments into one average measurement for the height at that distance. With that in place, what we can do is to go off and plot the actual observations, again as blue circles. That's what that little BO means there as the argument to plot. And we're going to use polyfit, as we have before, to do a linear fit to see if there's a linear relationship between the distances arrow has flown and its height above the target. Okay, so we're all set to go. Let's save this out and then run it and see what the plot looks like. So here we have the data. You can see it as the arrow flies from the bow over here to the target, and the target looks to be about at 1,080 inches from where it was released. You can see it follows a trajectory where it goes up and then it comes back down again. And here's a linear fit of a line to that data, and it's probably fair to say that the hypothesis that the arrow travels in a straight line from the bow to the target is not a good hypothesis. You can just see that this linear fit seems to really bear no relationship at all to the actual data points. So let's go back to our code and let's try a parabolic fit. And so what we're going to do is look for a quadratic equation that relates the distance to the altitude of the arrow. So let's get this code back into execution. So this is just an addition of fitting a second degree equation to the data. And let's see how that goes. So we're going to save this out and run it again and look at the plot. And yes, here we go. So this curve here actually looks like it fits the data pretty well. The jaggedness comes from the fact that we're just simply plotting the parabola only at the data points at which we actually had measurements. It would be possible to plot the parabola using many more values. Since it's a mathematical model, we could choose other distances that we didn't make measurements at, and then the parabola would look much more smooth. So that looks like a pretty good fit. And so we're sort of happy with that. Maybe what we should do, though, is to think a little bit about how do we measure the goodness of a fit. Is there some mathematical analysis we can do that would reveal that the line is a lousy predictor of the observations, whereas the parabola is a much better predictor? So how do we measure the goodness of a fit? Which one of these curves actually fits the data better? The quadratic fit or the linear fit. And we can tell by eye which one we seem to think is much better. Let's see if we can develop sort of a mathematical explanation of which one is better. So, I guess the basic question is, does the model fit the data? Are our predictions coming close? So let's start by talking about sort of a measure of the size of the errors that are being generated between the predictions and the observed points. So we can talk about sort of the variability of errors. So if we sort of start there, we can say, variability of the errors. How much are the errors varying? So here we can see that the errors are huge. They're big and they're small. And so if we sort of talked about a mean error, how much are we varying from the mean? Are the errors pretty much all the same, or are they big or the small? So we're talking about the variability of errors. And a standard measure of variability is the variance. And in fact, we've seen this. This is in fact just exactly the least squares, right? If we look at the error, which is the difference between the observation and the prediction, and we take the sum of the square of those errors over the whole thing, and then we do some sort of normalization here. So there's some sort of normalization constant, which I won't bother to put in. That would give us a sense of how much the errors vary. So if there was a small errors all around, then in fact the variance of the errors would be small. And we can say, well, that's good enough. We could just sort of take this number, and whatever its value is, a small value would be mean the model fit well, and a large value would mean that the model wasn't fitting. But the trouble is that if we're making observations in terms of parsecs, the errors may be small in parsecs, but as an absolute value the errors are sort of huge. So really what we want to do is to compare the variability of the errors to the variability of the original data. So we can use the same sort of measure of variability, the variance of the data, which is, again, some sort of normalization factor. And we're going to talk about the values of the observations relative to the mean observation. So that would be the variance of the data. And what we want to do is to sort of compare those, make a ratio of those two quantities to get a sense of how well the model is fitting the data. So the fraction of the variability that's not explained by the model has to do with the ratio of the variability of the errors, which is the part that we're not explaining with the predictions that we're making, over the variability of the observation. So think of this as sort of a normalization factor. And so this gives us the fraction of what we're observing that's not explained by the model. So that means that the fraction of the variability that is explained by the model is basically 1 minus that ratio. So the variance of the errors over the variance of the data. And this is a very useful measure. This sort of gives us a sense of how well the model is explaining the observations that we're making. And we hope that we're doing a good job, that the errors, variance in the errors is small compared to the variance in the data, which means that we're explaining almost all the changes in the data that we see. We're able to predict them. So this is given a name, R squared, and this is called the coefficient of determination. So when the coefficient of determination is close to 1, that means that the model is doing a good job of explaining the data. And when the coefficient of determination is very small, it's close to 0, that means that there's not much of a match at all between the model and the data. And we never expect R squared to be 1, because that would mean we had no error at all, and we expect most of our experimental observations to have some small amount of error. Let's put this observation into some code. So up here we've written a procedure that will compute the R squared value given a set of measurements and a set of predicted values. And so here we can see that we're calculating the sum of the squares of the estimated errors. And then down here we first compute the mean of the observed values, and then we compute the difference between the mean and the measured values and the sum of that squared. So we've left out the normalizing factor for the variances, since the two normalizing factors cancel on the ratio. So finally, we form that ratio of the variance of the errors over the variance of the data, and then we subtract that from 1 to get the r squared value. And then down here, what we've done is to modify try-fits into try-fits 1, and we've simply gone ahead and calculated the r squared value for each of the two fits and put that on our plot. So we're all ready to run that. That's the code down here. So let's save this out and then run it and see what we get. So now the plot is exactly the same as before, except that we've reported the r squared value for each of the two models. You can see the linear model, which we sort of suspected wasn't a good fit at all, actually has a very, very poor r squared. The variability of the data is not explained well at all by the linear model. However, the quadratic model actually has a very good r squared. So that means that, in fact, the quadratic model is explaining most of the changes that we see in the observations. The model predicts those changes. And there's a small amount of variance in the observations that's not being explained, and that comes from the observational errors. So the conclusion is that we can sort of use the r squared value to give us a sense of whether our model is doing a good job of predicting what the data is actually doing. So if r squared is close to 1, the prediction is good, and if it's not close to 1, then the prediction is less good, and maybe we should continue our search for a better model.